Okay, welcome everybody. Let's go ahead and jump right in. Welcome to day 4. As a reminder, we're using this sign-in sheet system to help the TAs just keep track of who's able to attend in person. So please, on your way in, sign in, grab a worksheet. If you didn't sign in on the way in, please just do it on the way out. So in today's lecture, we will wrap up our discussion of bonding models for organometallic and coordination complexes, and understand concepts like splitting energies and how that affects electron pairing and frontier orbitals. Then we'll transition into a discussion of the elementary reactions that coordination complexes and organometallic complexes can undergo. And so in terms of an analogy, this is like learning the alphabet and the phonics of organometallic chemistry. And then the rest of the class will be composition. So these are some of the fundamentals that will then apply in composing catalytic cycles. So let's jump in where we let's pick up where we left off last time. But before doing so, let me ask if there are any questions of points covered last class that can be clarified. It's not reading my iPad for some reason. So last class, we covered the different, sorry if this makes you dizzy, we covered the different coordination geometries, octahedral, tetrahedral, and square planar as 3 representative case studies, and in fact, 3 of the most commonly encountered geometries that you will be exposed to in this class, and then took a look at what the d orbital splitting diagrams look like for each of those geometries. So picking up where we left off, let me introduce a concept now called the spectrochemical series. And this is not something that necessarily falls out of first principles, but is related to first principles. And so let me first emphasize that the spectrochemical series is an empirically derived trend. So if you're asking again, what is the connection between this and some of the first principles we've covered so far in class, I'll just say this is an empirically derived trend. So there are some exceptions to the rule, and the key point here is to just have a general sense of the trends involved here. And the original characterization of the spectrochemical series was in the 1930s in the context of work on cobalt coordination complexes. You can get a flavor now for how important cobalt coordination complexes are in the history of organometallic chemistry. And the spectrochemical series is all about ordering complexes with respect to delta, delta being the orbital splitting energies. And the orbital splitting energy helps us define, or helps us anticipate and then back rationalize whether in a given organometallic complex may be high field or the splitting energy corresponds to the effect that the ligand field will have on the d orbital energies, and whether that is a high strength field or a low strength field, and thus how separated energetically those 2 orbitals are, and the consequences of that in terms of first row metals defines whether those will be so-called high spin or low spin. We'll define what that means very shortly. So here's what the overall trend looks like, going left to right from low splitting energy to high splitting energy. And some of the trends that qualitatively should pop out is that on the right are typically neutrally charged ligands those that are relatively strong sigma donors, and particularly those that are pi acceptors. And if you don't understand that terminology, we'll unpack that in today's class. And on the left are typically charged X-type ligands, and those that can engage in pi donating interactions that have a lone pair on the ligand that can donate to an unfilled d orbital on the metal of appropriate symmetry. So you can look at this empirically derived trend and be familiar with it, and we'll work through a couple case studies of how you can apply this. Now, there's also a trend with respect to the metal elements involved, and in particular, the oxidation state of the metal. So one thing that you can pick up on here is for a given metal, higher oxidation states have higher splitting energies. And that splitting energies also increase down a given group. And so let's apply this now to a, let me try to move this. A given case study, that of D5 iron 3 which has an octahedral geometry. And we'll apply this concept of the spectrochemical series and splitting energies to make a prediction about whether for a given ligand set, iron 3 will be so-called high spin or low spin, meaning high spin meaning that there's a large number of unpaired electrons, and low spin being there's a small number of unpaired electrons. And so let's walk through this case study here. We have 5 electrons to put into this d orbital energy diagram. The first case on the left will be this iron hexanitro or hexanitrate complex, and then on the right will be the hexabromide complex. Okay, so let's, and you can see that the key point here is that if we apply the spectrochemical series, we see that as compared to bromide, the NO2 ligand is a relatively strong field ligand. And the overall series, it's not one of the most strongly, but it's strong with respect to bromide. Okay, and so let's go ahead and fill in this electron energy diagram. Any volunteers here for the one on the left? Madison?
So you just start filling in all of them on the bottom set of orbitals. So you'd have 2 paired and 1 single.
Okay, so the first 3 are obvious. There's really only one logical choice, which is that you fill in each of the low energy degenerate orbitals. And then you have a competition. You have a competition between the Aufbau principle, which states that lower energy orbitals should be completely filled in first before going to higher energy orbitals, and Hund's rule, which says that if 2 or more orbitals of equal energy are available, electrons will occupy them singly before filling them in pairs. So you can imagine then that when this splitting energy is relatively small in magnitude, then the electron pairing energy can actually be higher than the energy required to occupy a higher energy orbital. So Madison, you said that I should fill in the next 2 electrons where? In the T2G level, and that would be only 1 unpaired spin. And we call this then low spin.
High spin, so they're going to be all unpaired and be able to go up to those higher energy levels.
Beautiful. Yes.
A question about the NO2 in the first case.
Yes.
Is that charged or?
It should be NO2. minus, and so you're right that I have this misdrawn, which has 3 plus. This should be 3 minus. Thank you for catching that. Thank you. And this discussion also connects to terminology that you'll hear in inorganic chemistry, organometallic chemistry, of diamagnetic and paramagnetic. Diamagnetic being complexes that in their frontier orbitals have no unpaired electrons, and paramagnetic that have that do have unpaired electrons, and this manifests itself in terms of paramagnetic complexes being difficult to characterize by some of our favorite analytical techniques like NMR. Okay, so let's apply what we just covered now in a few more case studies. So this one I'll give you a chance to think through on yourself. So this is problem of the day number 3 from the day 3 handout. So I'll switch over to that briefly. But if you don't have that with you, I can redrawn the structures that we're asking about here. And this just asks to predict whether a given complex, the 3 complexes shown, will be high spin or low spin. Cobalt, hexa aqua, 3 plus, nickel, tetra, cyano, 2 minus, or cobalt, and cobalt hexafluoride, 3 minus. So give that, let's take 30 seconds to think about that, and then I'll call on volunteers. I'll close this. Let's hand me eyes. So the disclaimer that I'll add here is that in the context of an exam, for example, if we ask something like this, we would try to give you a relatively extreme case rather than one that is going to lie on in an intermediate state that you might not necessarily be able to predict a priori. If we asked you about an ambiguous one, then we would ask you to explain your answer. Okay, so let's walk through this. Maybe we'll do this slightly out of order and discuss A and C first, and then B next, since A and C are both cobalt 3. Pranali, what do you think for A and C?
I think A is
Okay, could you explain your reasoning?
cobalt, the pre-oxidation state is, I think it was the highest spin the metals listed.
Okay, and then what about the ligand set?
And H2O is also one of the higher spin.
Okay, and then where did you come down on, let's go out of order here, C?
For C, I was actually just
Okay, and if you're coming down on the hexa aqua as being high spin, then I guess
it should be a little low.
the something that has a lower splitting energy, if you reduce it further, going from the aqua to the fluoride, then you'd expect that to still be high spin, right?
Yeah.
Okay, anybody get anything different for that? I think based on the information that's provided, that is a reasonable answer, but because we gave you both of these together, the hexa aqua and the hexafluoride, the hexa aqua just pushes the energy levels high enough that it can actually be low spin, although I wouldn't necessarily expect you to predict that just from the information provided low. So whatever you came down with there was fine. And then B, Shenghua, what did you come up with?
I think it's high spin.
Well, let's take a look. So I guess we don't have the cyano here on the spectrochemical series, but I can tell you that it's relatively strong splitting energy. I should add that for future more straightforward answer. So you revised your answer to low spin, is that right? So splitting energy is relatively high. That means that the electron pairing energy is small relative to the Aufbau principle going to higher energy levels. So you fill up those energy levels.
Is the spectrochemical series like quantified at all, or is it all just kind of less than, less than, less than? Like, are there numbers associated with this so that it becomes a little less sort of vacuous?
Well, I think it's complicated by the fact that it would change, you can quantify it for a given metal with a given ligand set, and then you can quantify it for a given ligand set for a metal. But then the cross correlations don't always line up directly. So I think the qualitative ordering is about as good as it gets here. Now we'll talk about more systematic ways to characterize ligands later in class.
So Curie, just another question.
Yeah.
Real quick. I missed the last lecture, but I'm trying to make sense of this. So you said that although cobalt 3+ typically leads to like a high spin complex, in this case it's low because water is a relatively like middle ground ligand. And like in particular with cobalt, I guess it's a little bit oxophilic, so it brings it like that molecular orbital gap to something low. Like that'd be a good way to rationalize it.
Yep, I think that makes sense.
On that note, I'm still a little confused if the fluoride is closer to the low splitting end of the spectrum. Why, if it's the same metal center, the like aqua complex would be low spin, but the fluoride one would be high spin.
So we can we'll draw out these two. Let's draw out these two case studies of the orbital diagrams. So first, I guess I should have done this first, but what is the d electron count here? For the, let's say for the top case, cobalt 3+ should be what? 6. 56, and then the iron 2-, sorry, the iron +2 oxidation state is. Okay. So let's consider the 2d6 cases. So in the case where we have a high splitting energy, low spin, I'll draw this in an exaggerated way. And fill these in. And in the case where we have a low splitting energy, so the comparing those two, fluoride versus aqua we're saying is a higher splitting energy compared to fluoride. So reducing the splitting energy now gives you the opportunity to occupy the higher energy orbitals, which ends up making a high spin. Does that make sense, Tom?
Thank you.
Curie.
Yes.
So if the ligands are kind of midfield, is there like a general rule of thumb to determine whether it's high spin spin
Yeah,
out.
that's a good question, Christine. I think in general, this is the kind of thing where you'd say you have to do the experiment to be sure. I think if you're given some benchmark data of near neighbors and their properties, then you can make more educated guess. But I would say in general, it's the kind of thing where you have to do the experiment. Okay, very good. And then the one point I want to make here too is that this question of high spin, low spin is really most relevant when we're talking about first row metals. So when you go to second row, third row, so down the series, nickel, palladium, platinum. Nickel has this phenomenon of being able to be high spin, low spin. When you go to palladium and platinum, that's a rarely encountered, almost never encountered. So this is a phenomenon unique to the first row, more or less. And so again, if in a context of a problem set or an exam, you're given a second or third row metal, immediately alarm bells should be ringing that you're probably not going to be in a high spin. Okay, another concept that I'll introduce briefly, sorry, I'll leave it here in case you want to jot this down, is Jahn-Teller distortion. I won't say too much about this. The underlying science here is quite interesting and something we could spend a long time on, but I'll just define this concept and move on. Jahn-Teller distortion refers to spontaneous symmetry breaking in systems where you have an unpaired spin. So we can consider this case of an octahedral metal complex that's D7 and D7 low spin. And spontaneous symmetry breaking arises from the fact that when you have a set of degenerate orbitals, in this case, two degenerate orbitals that are unequally occupied, that the complex will prefer to break symmetry in order to get the filled orbital to a slightly lower energy level. So in the case of, again, this octahedral complex, Jahn-Teller distortion will manifest as broken symmetry between the dz squared and dx squared minus y squared orbital, which geometrically in terms of the complex will lead to elongation of the two metal ligand bonds that lie along the z-axis. So you would go from a true octahedral geometry to a distorted octahedral geometry that we would call square pi the pyramidal, such that the dz squared orbital now lies at slightly lower energy compared to the dx squared minus y squared. Any questions on Jahn-Teller distortion or spectrochemical series, low spin, high spin? Okay, so let's move forward now and discuss ligand field theory. And I will first add the caveat that our discussion of ligand field theory will be somewhat brief. Ligand field theory is something that's not really covered in the Hartwig textbook. It's only covered briefly in the Crabtree textbook. You could take a very deep dive here and just discuss ligand field theory for multiple classes. And we'll have more of a surface level overview. If you want more reading material on this particular topic, then come see me and we'll help you get all that you're looking for here. But what it is in essence is that the superposition of MO theory, which you're familiar with from Gen Chem, and crystal field theory. And it essentially arose as a need to account for the fact that in this treatment of crystal field theory, we said we make this assumption that all the ligands are point charges that exist in space and they apply electric field. But this is not reality. We know that a fluoride ligand has a very different effect in terms of its bonding interactions than a carbonyl, a CO ligand, because of its molecular orbitals, the molecular orbitals of the ligand itself. And so this superposition now allows for a more accurate description of bonding and the energy levels that are involved in frontier orbitals. So you can think of ligand field theory in a general sense as the superposition of the two systems that we've covered up until this point. And so we'll consider first the simplest case of an octahedral ligand set that is composed of pure sigma donor ligands. And you could take this one step further by examining ligands that have more complex bonding, but we'll just leave it at this for the time being. And I'll try to walk through how this manifests itself in terms of the overall MO depiction. And the first concept I will introduce is called the symmetry adapted linear combinations, or SALCs. So symmetry SALCs of the corresponding ligand orbitals, or the vibrational displacement vectors. And the terminology here seems a little bit complicated, but in essence, what this is we're building up these SALCs in analogy to how we build up molecular orbitals from atomic orbitals that you cover in Orgo 1 or Orgo 2 in your undergraduate institute. So we know how to put atomic orbitals together to arrive at a MO depiction, and here we're just treating the ligands in a hand wavy way as atomic orbitals, and then putting them together in an MO depiction. And so again, if we consider these pure sigma donors as the representative case study, then you can combine an octahedral ligand set of 6 sigma donor ligands to SALCs that have 3 types of symmetry that are described by A1G, T1U, and EG. And you don't really need to strain your brain too much to quickly recognize that there's an important connection here between the symmetries of these SALCs and the orbitals of the metal that can be involved in bonding. So the A1G, what type of orbital does that look like that would nicely formed a bonding interaction? An s orbital, right? That is spherical in nature. The T1U, what type of orbital does that look like? That would form a nice bonding interaction. A p orbital. But someone say a p orbital, right? And then the EG, what does that look like? It would form a nice bonding interaction. Well, maybe the one on the left, like a dz squared orbital, and maybe the one on the right, like a dx squared minus y squared orbital. So without even digging into the details, we're seeing that there's a nice alignment here between the shapes of these SALCs and the shapes of the orbitals that are now metal centered that can form bonding interactions with these ligands. And so now we'll see how this actually manifests in terms of an orbital diagram. So the case study we'll consider here is titanium hexa aqua 3+, but you can consider many, essentially any octahedral complex that has ligands with predominantly sigma donating character, and you'll arrive at the same overall depiction. Okay, so this looks complicated, but let's try to unpack this. So on the right side is the SALCs from our previous analysis, and on the right side are, on the right side are the SALCs from the previous analysis. On the left side are the orbitals that are involved in bonding to the metal. The first thing to appreciate is that the filled ligand orbitals are the lower energy than the orbitals that are on the metal. I think that naturally falls out of the fact that the orbitals on the metal have a higher principal quantum number. And so we said that the 3 types of orbital symmetry, the SALC orbital symmetry that we're bringing in here, the SALC symmetries that we're bringing here are A1G, T1U, and EG. And then we already talked about how those are going to form bonding interactions with the corresponding orbitals on the metal. So let me try to highlight that here. EG, we said there were two orbitals that had that. And you'll notice from that previous analysis, the first thing to point out is that there are 3 d orbitals that never came up in the discussion. Those are the dxy, dyz, and dxz orbitals. So those are not going to be involved in bonding interactions, at least first approximation, and those are then going to be the 3 orbitals. Color here, yellow. These 3 orbitals here. So the Salk of A1G symmetry is going to form a bonding interaction with the 4s orbital. The Salks of T1U symmetry are going to form bonding interactions with the 4p orbitals. We have 12 electrons to distribute, and then likewise the Salks of EG symmetry are going to form bonding interactions with the 3D the 3D orbitals mentioned. And so then those we fill in with 12 electrons. Titanium here, if you do the math, is a D1 metal, so it has 1 filled electron. And then so the EG orbitals are forming a bonding interaction and then an anti-bonding interaction. And then, of course, all of the orbitals that I described already form a bonding interaction and an anti-bonding interaction. I didn't draw all of the anti-bonding interactions here, but you can see on the right how those are. And so, in essence, then now we have, in terms of the orbitals that are involved, X, Y, Z, XZ, X, Y squared, and Z squared. And look what this ends up simplifying to. It is essentially exactly the same frontier orbital depiction that we get from simple crystal field theory. So that's really the upshot here, is that ligand field theory is a more complex treatment that will end up giving you a similar frontier orbital depiction as crystal field theory in many in many of the cases here. Are there any questions on this? Camille?
For the ligand orbitals on the right, I'm confused why they're not all the same energy before they interact with them.
Yeah, that's a good question. They are of the same energy, but I couldn't go far enough to the. But maybe I should redraw that. Are there any questions on that? Okay, so now let's look at kind of a cross-section of ligand field theory. And we'll just focus on molecular orbital interactions between metals and ligands in a really more of a zoomed in way, because I think most of the key insight you can get from looking at this level of granularity. And so to kick off this discussion, we'll define more rigorously some of the terms that we have used already in class, but now again we'll define this more rigorously. So in terms of the types of bonding that we encounter in organometallic complexes, there's a sigma bond, which just refers to, remember this nomenclature, sigma pi, and then delta. This just refers to the symmetry of the orbitals that are involved in bonding, directly analogous to what we learned about main group elements. So sigma bonding refers to a donating interaction of sigma character between, for example, a lone pair of this amine and to a filled orbital to an unfilled d orbital of appropriate symmetry, dx squared minus y squared or dz squared. And so that's pretty intuitive. Sigma bonding can be with a L-type ligand, it can be with an X-type ligand. There's one point of terminology that's a little bit confusing, which is that pi-based ligands like alkenes, alkynes, etc., can be sigma donors. So they can, despite being of pi character on the ligand, in terms of the bonding interaction with the metal, it would be defined as a sigma bond. Pi systems can engage as sigma donors as well. Oh, my Apple Pencil is of low battery, so we'll see how this is going to work. Screen sharing is paused. So share. If I can charge this pencil off of my phone. Okay, and then the other type of bonding that, again, we've discussed a little bit already in class is pi bonding, and this can come in two different flavors, defined by whether ligands are being donated from the ligand to the metal or from the metal to the ligand. So let's first consider the case of a chloride ligand. And so in this case, we have sigma bonding between the lone pair of the chloride ligand and the, bless you, of the metal orbital, and then pi back donation that comes from the lone pair of the chloride to an unfilled d orbital on the metal of appropriate symmetry. So this would be, so if this is the dz squared orbital or dx squared minus y squared, then this would be dxy, dyz, x. So the key point here is you have filled non-bonding electrons here. So this we would call pi donated. And then you can also consider the opposite case. So let's consider the bonding scenario with olefins as ligands. So as we just said, these can be sigma donating. But now you have a pi star antibonding orbital on the ligand that is of the appropriate symmetry to accept electrons from a filled d orbital on the metal. So, that orbital is filled, it can donate electrons into the pi star orbital. And these are called pi accepting. Pi acceptors. And we talked before briefly about how the bonding situation between alkenes and metals was initially quite unclear and was ultimately defined in the middle of the 19th century and led to this model that we accept now called the Dewar-Chat-Duncan model, which effectively is what I just said, this sigma donating interaction and pi back bonding interaction. And so one of the consequences here is that by virtue of being a pi accepting ligand, there's a these ligands that can engage in pi back bonding will form a stronger metal to ligand bond. This bond almost starts to have double bond character because you have donation going from ligand to metal in the sigma direction and metal to ligand in the opposite direction. So it becomes a stronger metal ligand bond. And then in this case, a weaker bonds within the ligand because you have this anti-bonding orbital being pocketed. So weaker CC double bond, which you can see clearly from X-ray crystal analysis of these corresponding pi alkene complexes. Okay, so let's consider another commonly encountered class of ligands. So if you've ever done a cross-coupling reaction with palladium, likely you used a phosphine ligated palladium catalyst. So we're all at some level familiar with phosphines as ligands to metals. And I think the sigma donating character of phosphines is well appreciated, but an equally important, but perhaps less appreciated aspect of phosphine ligands is that they're also pi accepting ligands. And at first glance, you might look at this and say, okay, what orbital on the phosphorus atom is actually going to allow for pi back bonding from the metal? And you might conclude that it's the 3D unoccupied 3D orbital, but that's not quite right. In fact, a better way to think about it is that you're donating electrons from the metal into a sigma star antibonding orbital between phosphorus and carbon, or the actual most accurate depiction is that there's this orbital mixing model between a sigma star antibonding orbital and the 3D orbitals that we've depicted here, and that's the orbital that's accepting electrons from the metal. We'll talk more about phosphine ligands and their special properties in the ligand design and ligand parameterization lecture. So I won't say too much more about that now, but wanted to give you that preview for the time being. Okay, so let's also now consider other types of ligands that can engage in pi back bonding in situations where pi back bonding is a little bit less obvious. So we'll first consider the case of H2, which I think is an interesting one. So the sigma bonding orbital here, which I'll represent in this way, which is filled, and engage in a donating interaction to the metal. And then the sigma anti-bonding orbital, which we'll just draw with the opposite symmetry here, can engage in pi accepting interaction. So sigma orbital and so there are some interesting consequences of this that you can read out then in solid state. So dihydrogen itself has a HH bond of about 0.74 angstroms, but HH metal complexes, which we call sigma complexes, you can see significant bond lengthening in solid state structures. And I'll point out that making these types of measurements is by no means trivial. You might just think, okay, we get a crystal structure of a sigma complex and go over to UCSD and get the bond lengths. But remember that H atoms do not diffract X-rays strongly. And so to pin down these types of bond length measurements with any level of precision, you need to turn to single crystal neutron diffraction. This has been done before. That's how these values were determined. But that is a whole other can of worms. I've actually done single crystal neutron diffraction myself. And you need to go to a specialized synchrotron to do it. And so it's not necessarily for the faint of heart. And then you can imagine in a very extreme case, remember, so in this case, we're populating this sigma star antibonding orbital. So what does that mean in that if you take that to the theoretical limits and you're donating into an antibonding orbital, eventually you will lead to sigma bond cleavage, and that's an elementary step that we call oxidative addition. Okay, so another very important ligand, arguably one of the most important ligands that we'll cover in class is CO as the ligand. And so CO engages as a sigma donor and a pi acceptor. So let me draw that out. Have a lone pair here that is the sigma donor. And the pi acceptor is a CO antibonding pi antibonding orbital. Just draw this again, emphasize which orbitals are filled, which are empty in this case. And so in the context of CO, back bonding will lead to weakening of the CO bond. So in the gaseous state, we know carbon monoxide has triple bond character. Now, when you coordinate to, and that can be read out by IR with a stretching frequency of around 2100 wave numbers. So now when you coordinate to the metal, depending on how extreme the bonding is, you could, like the way I like to think about it is in a really extreme bonding scenario, you go all the way to, so let's consider the two limiting scenarios here. One is you have a metal CO, and the CO is basically still triple bond. And the other is that the back bonding interaction is so strong that it becomes almost a double bond. And now your CO is a double bond. And so we know, of course, from freshman Orgo that CO double bonds have a characteristic stretching frequency of, let's say, between 16 and 1700 wave numbers, ketones, esters, depends on the carbonyl compound you're talking about. But if we think free CO is about 2100 wave numbers and a CO double bond from classical organic chemistry is 1700, then where the CO stretching frequency of a given metal carbonyl complex lies allows you to see how strong the back bonding interaction is. And then also just to quantify the strength of the bonding interaction between metal carbonyls, it can range quite a bit from as weak as 10 kcals from to as strong as 40, and it becomes stronger with increased back bonding. So this is the scenario with increased back bonding. The more double bond character that has, the stronger it is. And I think that is pretty intuitive. So we can also take a peek at just a simplified MO diagram here between CO and a MO diagram of a metal carbonyl complex. And again, one of the features that the first feature that should pop out to you is that the filled ligand orbitals are of lower energy than those on the metal. And so the lone pair can form a productive bonding interaction with the dz squared or dxy squared orbital, as shown on the bottom. And then the dx squared minus dxz, dyz, or dxz orbitals can form a bonding interaction with the pi star anti-bonding orbital of CO. So this is sort of the quick and dirty MO diagram for metal. And so there are, we've talked about concepts like isostructural, isolobal, and electronic. And so there are a whole suite of ligands that in fact are isoelectronic to CO. And this is interesting to as a thought exercise that you could cover this page, or this part of the notes, and see how many you can come up with yourself. But they come in many different flavors, from positively charged to neutral to negatively charged. And the key point when we say something's isoelectronic, it just means that it has the same frontier orbitals that can engage in the same type of bonding with the metal. And I put this in here as kind of a preview, so these references will be included in your readings for today. And our neighbor, Josh Figueroa at UCSD, will be one of the guest lecturers for day 9, has looked to done some really pioneering work on some of the more exotic isoelectronic ligands to CO, including this interesting BF, linear BF ligand that we'll get to hear about in his lecture. Okay, so let's wrap up this discussion by turning to the last problem of the day, number 4 from the day 3 handout. And I will share that handout and then keep it up because I don't have all of the this will give me a chance to charge my pencil. So this asks you to consider 5 different pairs and try to rank them in terms, or try to make a guess, an educated guess about which will have a higher CO stretching frequency. So the first thing I will say is this is always a little confusing to me. Higher CO stretching frequency, what does that mean? That means that it has more, higher means more triple bond character, which means weaker back bonding. So which of these pairs has higher CO stretching frequency, and briefly explain your reasoning. Let's take 2 minutes to work through those examples, discuss with your neighbor, and then I will ask for volunteers, or I will volunteer you from
On B, should that be trimethyl phosphite?
that should be trimethyl phosphate. Thank you for catching that. Is that right, Nathan? Yeah. Was Nathan not here?
Is B?
B should be trimethyl phosphite. Right? I think we have a subscript missing. If you didn't catch that exchange, this is 2 over 3.
Also A.
A, okay. A has P. So, and that reminds me, one administrative announcement I can make is that we'll have all of the resources that you need for class available on our lab website under the resources page by noon today. We just had to put that page up and get the YouTube video. So if you want a one-stop shop where we don't have to go through Canvas, you can just find the videos, the handouts, the worksheets, all of that will be online on our group webpage. Are we ready or do we want another minute? One more time. All right, let's jump in. And if you're still not sure of any of them, then hopefully it will come out through discussion. And I will just, because of this pencil charging issue, I'll just do this on the chalkboard and I'll try to do it in the view of the camera. Okay, so part A, what do you think there? Zijun, do you prefer Annabelle or Zijun? Annabelle. Okay, Annabelle, what do you think?
So the first complex is a titanium 4 species.
Okay.
Second is the second one has more electron density on the metal, it's going to have more back bonding, so
Okay, so I think you're spot on here in your thinking, but let's take this one step further. So you said the one on the left is titanium +4. How many electrons? What's the d electron count of titanium +4? Aha. So can a D0 metal engage in any pi back bonding? No back bonding. So it has no electrons to give. It's tapped out. So that's a key principle here is that maybe I'll actually draw that on the notes here. So you have that. D0 metals cannot engage in pi back bonding. I know, I'm just going to put it here and then it will show up when I. Okay, so what did that lead you to conclude would be the correct answer?
the first one has higher scale stretch frequency.
The first one is higher. Okay, so I'm just going to say left or right as we go down this answer. Any questions on that? Okay, how about the next one there? Christine, what do you think?
I believe the first one is rhodium +1. And then the second one also is rhodium +1. So both would have one count.
Okay.
I'm not sure where to go from there.
Okay, that's a great start. So you set it up nicely. So the d electron count's the same, oxidation state's the same. So what is changing between the two ligands? You have hydride versus chloride, and you have triphenylphosphine versus methylphosphite. And so this is going to come down to your analysis of those ligands, how good of sigma donors versus pi acceptors they are. So the first question really came down to oxidation of the metal. This one's going to come down to the properties of the ligand. Anybody want to chime in as an assist here?
I think for the complex on the left, you have the hydride, which is a good pi donor.
The hydride will be a good sigma donor. Yeah.
Also, you have triphenylphosphine, which is also a good sigma donor.
Okay.
So you have more more electron density on the rhodium center that would facilitate the high back bonding to the C.
Okay. So let's compare. I think Wenji had a good explanation. I'll just restate that. On the left, we've got a hydride ligand, and triphenylphosphine, both of which are pretty good sigma donors. And we'll unpack this more in the ligand design, ligand properties lecture. And then on the right, you have chloride, which is an okay sigma donor and pi donor, but not great. And then a trimethylphosphite, and we'll learn later that phosphites are pretty good pi accepting ligands and relatively weak pi donating. So you've got two strong sigma donors versus something that is more pi accepting in character. So then the conclusion is, what did you say?
The right one.
Okay. C, how about Anthony?
I said the iron 2-, so it's a little bit more electron rich.
Okay, and so we're saying iron is, now we've got the same ligand set and different metals, and the one on the left is monoanionic, the one on the right, the cobalt complex is monoanionic, the iron complex is dianionic. And then which of those is going to be a better better engage in pi back bonding?
I would guess the iron only because it's got more electrons.
Okay, the iron, and will that lead to a higher or lower CO stretching frequency?
Lead to more double bond character.
Or double bond character, which would be lower. Okay, so the answer
Right.
is left, because it's asking about which has higher CO stretching.
Oh, of course, yeah.
Yeah, that's what I always get the same thing mixed up to. I kind of like do it in all directions every time. Beautiful. And in addition to that, remember that if you compare cobalt to iron, cobalt is also a little bit is more electronegative. So it's going to hold on to its electrons more tightly. Okay, now D, Dylan, what do you think?
I'm not sure. I want to say that it would be the left one. I just feel like it would have more electrons to.
This one is a tricky one because you're changing multiple things. You're changing the metal, you're changing the ligand set, and you've got to try to
So
make them.
the manganese
which
is
more important.
+1 and the tungsten is +2. I guess then tungsten would have less electrons to like back donate. So the right one would have the higher frequency, so it'd be less back bonding.
So your answer was the right, or the
Final answer is right.
final answer is right. Okay, did anybody get anything different?
Left. Oh, sorry, no, right. I mixed it up.
Anybody get left? We want to play devil's advocate here.
Manganese is the first row transition metal, but tungsten is the third row. So potentially it has it's 6. It's probably those electrons are further from the nuclear center, so that those are less constrained, and they can probably participate better in that bond.
Okay. So you're
I'm guessing the left.
okay. What else does the left one have going for it? If we compare the, remember CO is archetypal pi accepting ligand, and the one on the left's got 5 of them. The one on the right's got 4 of them. The one on the left has a relatively weak sigma donating fluoride ligand. Fluoride's not a great ligand for metals because it just wants to, it's very greedy. It wants to keep all the electrons for itself, as compared to 2 iodide ligands, which are more happy to give up their electrons. So in terms of the ligand set, we would say the one on the left has more accepting character, the one on the right has more donating character. And so I think there are, this was a great discussion, and you could use first principles to come down on either side, really. But in the end, the ligand sets carry the day here, as well as what Wenji pointed out. So left is the right answer, and then the last one, yes.
I don't understand how it being a higher up on the periodic table corresponds to that, because shouldn't it have better overlap with the orbitals if they're similar in energy? If you're comparing a 3D orbital versus a 4 or 5D, shouldn't the overlap with CO be better? Then you have more back donation.
And if you have more back donation, then the bond will be weaker and
Or it should be
shifted more to lower frequency, right?
right. So then shouldn't it be right, not left, for the higher CO frequency? I'm saying, shouldn't manganese as being a first row transition metal should donate better? Maybe I'm mixing the trends here.
I think Wenji's argument was that the tungsten should have higher energy orbitals that are able to gauge to stronger bonding to carbon.
Oh, I was under the impression that bonding to carbon is better with higher transition metals because of the relative orbital energy of 3D versus 5 or 4D when it's overlapping with a carbon sigma or pi.
Yes, but then wouldn't you conclude that there's going to be a weaker stronger back bonding when you have stronger bonding interactions in general?
Yes.
Yeah, which would lead to a lower CO stretching frequency.
Right. So then tungsten should have a higher CO frequency.
Tungsten should have lower because it's more. There's
I'll
more
just
back
think
bonding.
about it on my
Yeah.
own.
This is the exact same thing that goes through in my mind every time. Better donor, weaker donor, upfield, downfield, all these things. Okay. Why don't we talk about it after class, Alex, if you want to go through it. Or anybody who wants to discuss any of these further, of course, you're always welcome to stay after class. Wenji, why don't we do the last one here?
I'm thinking you have on the left you have a plate of platinum 2. On the right you have a nickel 0. So I think nickel 0 has more d electrons. So based on this principle, I would guess the one on the left may not be as back donating as the right one. So the left one may have
Your vote is left. Anybody get right for this? And want to argue the opposite? Again, this is the bottom ones are the more confusing because you're changing multiple things, right? You're changing metal, oxidation state, ligand set. And so, you can probably convince yourself differently here. Although I think
Sigma donor, right?
phosphine is a stronger sigma donor
So I don't know if I'm
and it's a lower oxidation state. So in general, you've got more electron density on nickel than you do on platinum +2. I think in this case, you're changing multiple things, but most of them argue in the same direction, perhaps with the exception of the row of the metal involved here. Okay, any questions on this? We'll have a chance to do more examples in the homework and throughout class. We'll review this topic. We'll come back to it. So if you're not clear, then you're not. We're running a little bit behind, but that's okay. We're to have good discussion and just blindly charge through the notes here. So we're actually going to directly shift now and keep the discussion going and shift into the next problems of the day, 1 and 2, which kick off the next set of lectures. So I'll share it here briefly, and then I'll turn over to my iPad. In the interest of time, we'll maybe just do the first one quickly as a class together, and then the second one I'll give you a minute to think about and discuss with your team or with your neighbor. So let me switch over. Okay, so the first question asks about the strength of the bonding interaction between the metal and ethylene here. And this is going to follow a similar theme to one of the problems we just countered in terms of CO stretching frequency. So first, let's just quickly do the d-electron counts for these two metals on the left. How about Jahn-Teller?
So the first one is zirconium 4 plus.
Okay.
So it has 0 d electrons.
Aha. Okay. And the one on the left?
And the CP ligands give 12. The 2 CP ligands give 12 electrons, and the methyl give 2, and olefin give 2. So it will give 16.
Oh, perfect. Okay, you did the electron count too. Great. Okay, and the one on the right?
Zirconium 2, so it's D2. And the CP ligands give 12, and olefin give 2. So it also 16.
Okay. So what's the key difference here you want to highlight as it pertains to strength of bonding interaction? Which is going to have stronger bonding interaction with
The
that?
right one, because it has stronger pi bonding.
Aha, okay. So we've got, again, a similar case to the one that we covered with Annabelle. D0, it cannot engage in pi back bonding. So as compared to the one on the right, which can engage in pi back bonding. And remember, in an extreme case, you can think of pi back bonding as populating a metallocyclopropane form, which then has two bonds to it. And so the one on the right is indeed going to have stronger bonding interaction. Thank you, Jahn-Teller. Okay, now let's consider problem of the day number 2 from the day 4 worksheet. And this one will ask you to rank in terms of the dissociation constant, the ligand set, or the series of ligands shown here: triethyl phosphite, triisopropyl phosphite, trimethylphosphine, this triaryl phosphite, and then these 2 triaryl phosphites. So 4 of them are phosphites. That's the first thing to notice, and then 1 is a phosphine. And then we can think through their different steric and electronic properties and make an assessment about how this is going to affect their propensity to occupy the 3-coordinate form, or adopt the 3-coordinate form versus 4-coordinate form. So take a minute to think about that. This is one where, in the absence of any data, you could potentially come to some different conclusions. So whatever there are different ways to think about this that are still reasonable. Okay, let's take 30 seconds and then discuss with your neighbor, please. Okay, Yushin, what do you think here? Explain your reasoning. You prefer to go by Yushin? Let's just get something down. If you're not totally comfortable with it, I'm sure you're not the only one. So let's get something down. Left to right in terms of lowest to highest KD. Sure, perfect. Let's just get the discussion kicked off.
Lowest KD would be
Number 3 is the lowest. Okay, then what?
then number 1, number 2,
1, okay. 2, you said, and then what?
number 4 and number 5.
4, 5. Okay, and explain your reasoning.
Well, I think you still need to consider the pi back bonding, if that is the case, and if the pi back bonding is stronger, then the KD would be like higher because you tend to dissociate faster.
Okay.
Metal ligand bond is weaker.
And I choose number 3 as the lowest KD because the biggest is weakest pi bonding and strongest ligand metal bond.
Okay. Did anybody get anything different? I'm sure somebody got something different. Alex, what do you think?
I don't have a full perfect ranking, but I would say triphenyl phosphine is the highest KD.
Okay.
Phosphites are better pi backbonding acceptors, so you're going to have stronger metal ligand bonding. So the KD is going to be the highest for phosphine versus phosphite.
Okay.
Within that, I just grouped the alkyls and the aryls. I'm not sure how they relate relative to one another, but I would say KD of the isopropyl phosphite is going to be higher based on sterics. They're electronically fairly similar.
Okay. So that's ethyl versus isopropyl.
And I would say 5 is greater than 4, but I don't know how those fit in relative to 1 and 2.
So I think there are some here that you could reasonably order, but to do the whole series without any data is admittedly challenging. Nathan, do I have this right here? Can you check?
I think the middle one should be 2. Like 1, 4, 2, 5, 3.
So this is the correct order. And I think there's a couple of things to consider here. So what is the relative role of sterics versus electronics in this series? Sigma donating versus pi accepting. It turns out that the sterics have a dominant role here. So how do we know that? Because this is the exact same trend as cone angle. What does cone angle mean? That's a parameter that defines how bulky the phosphine is that we'll cover in a later lecture. So that correlation tells you that sterics are playing a dominant role here. And then if we go through the series, we can see the triphenyl phosphine is the bulkiest. Phosphite, remember that all of the steric bulk, you have one atom bridge in the form of this oxygen that's going to push it farther away from the metal center, which will lead to a smaller cone angle here. And then I think you should be able to rank the alkyls with respect to one another and the aryls with respect to one another, but how they fit in with respect to across is difficult to do without any data. But this is the okay. Any questions on that? Okay, so let's jump ahead then to ligand substitution. So it's this.
Question.
Yes, please.
So why would 4 be less than 2? I guess, yeah, how do you?
Yeah, that's one. I think if you didn't have data, that's hard to make a comparison. I think that we know that that's what the data says. So I can give you a summary of what we know from the data. But to make that comparison is not easy. You know, you could probably try to, in your mind, think through what's bulkier, an isopropyl group or a phenyl group, just on a steric argument. And phenyl groups have this property of being a little bit less bulky than you think when you draw it out, because they can often rotate out of the way. Whereas isopropyl groups, they're kind of like always bumping into something. They can rotate out of the way to some extent, but then they're still bumping into something. So the ability of aryl groups, when they're not orthosubstituted, to rotate out of the way gives them a smaller steric profile than you might expect from the number of atoms that they possess. Okay, so let's talk about, with our remaining couple minutes, we'll talk about ligand substitution, which I think is the simplest elementary process that organometallic complexes can undergo. And this comes in two different flavors, associative and dissociative. And these roughly parallel the characteristics of SN2 versus SN1 substitution and main group chemistry that we're comfortable and familiar with. And so let's first cover associative ligand exchange. This usually takes place with 16 electron complexes that can afford to accept another ligand to still be within the 18 electron rule. And so often, and kind of a generalized form of associative ligand exchange is shown here, where a 16 electron complex, so think here, platinum 2, platinum 2, rhodium 1, will form a bonding interaction with an incoming ligand to get to 18 electron complex, and then kick out one of the original ligands on the metal to form a new complex. There are some exceptions to this rule of 16 electron complexes being able to undergo associative substitution. And one of the exceptions is shown here. And so how might this be happening? We have this 16 electron rhodium bis carbonyl CP complex that is still able to undergo associative ligand exchange, and we'll talk about how you can use data to determine whether something might be associative or dissociative. This is believed the data suggests is associative. How is this happening? Shenghua, you've almost got your hand raised.
Ring slippage of CP.
Ring slippage, okay. What does ring slippage mean? So these CP ligands possess the ability to toggle between the eta5 state and an eta3 state. The eta3 state you can think of as being essentially an al ligand plus a bonded alkene. So it's bonding just like an al group here now. And in so doing, it frees up a coordination site going from, well, I kind of like this. So this is more. So it frees up a coordination site, becoming 16 electron, and allowing the new incoming ligand to come in. Now, oftentimes this is thermodynamically uphill because you imagine you're breaking the aromaticity of the CP ring and going to this al form. So you can't, in many cases, you can't observe this type of intermediate, but you can infer that it's there. There are some exceptions to that, though. And one is the so-called indenal effect. The indenal effect is when your CP is not a simple CP, but in fact an indene. And this was first, the mechanism was first proposed by Basolo in the 60s. And so in an indenal system, actually, when you toggle from eta5 to eta3, the remaining area here, I guess I should have drawn this out. Now you actually restore aromaticity within the non-coordinating arene. And this leads to a 10 to the 8th rate acceleration. Relative to CP itself. And this type of process is called a haptotropic shift. We talk about hapticity, eta5, eta3. So this is called a haptotropic shift. And we'll just close out here by showing an example of the indenal effect from the modern literature. This is actually an Angevante ASAP paper. If you click on Angevante and you do a Control F indenal effect, you will find this paper. So I couldn't help but highlight it. And so this involves a bunch of stuff that we haven't covered in class. So I'm getting ahead of myself a little bit, but I'll just try to give you the upshot here. So has anybody who's familiar with this general area maybe want to provide the structure of the product here? What did you say, Shenghua?
You
Acetamide, you said.
yeah, cyanide, the CH, the ortho position.
So this is a nitrine precursor that contains, this is called the dioxazolone. I guess Yushin is probably the expert in the room here, more so than me on this type of reaction from his undergraduate research. But these types of, these are nitrine precursors. That slow off CO2 upon coordination to a metal and then generate a nitrine this way. So this is a CH amination process. And again, these details, I don't expect you to follow all of them at the moment, but the point I want to make is that in this paper, which covers a lot, actually, I'd encourage you to read it because there's also a lot of CO stretching frequency data for electronics of CP. That's a great way to practice that concept. In this paper, they show some rate data comparing the CP star rhodium complex. And so this is an example of a mu2 bridging chloride that we've talked about, represented in this way here. So it's the precursor is a dimer with 2 bridging chlorides. It compares the CP star with an endenal star, and you see significant rate acceleration at 2 hours with the endenal catalyst quantitative conversion compared to the CP star, only 25% conversion. And as the explanation for this, the authors invoke post-CH activation that the endenal star versus CP star, the endenal star is able to open a coordination site to allow this nitrine precursor to coordinate, whereas the CP, for the CP star, that process is higher energy and thus slower to take place. And so that is an example from our chemist of the day, who I'll highlight and then we'll be done, who is Australian. I think one of the first Australian that we've highlighted in the Chemist of the Day series since doing this class, Daniel Creepenow from Monash, was educated his PhD at Deakin University in Australia, with Fred Pfeffer and Scott Stewart, and then did a postdoc as a Humboldt Fellow at Aachen with Karsten Ball. He's been involved in developing CH activation reactions of this flavor, particularly these unusual ones that involve acyl silanes as directing groups. So as you can imagine, these are interesting synthetic building blocks, but they're quite sensitive. So the chemistry you need to develop has to be quite mild. So this is a nice example of taking advantage of the endenal effect to allow the chemistry to take place under mild conditions with a directing group that's susceptible to deconjugation. Okay, let's wrap things up.